Hi everyone. In this video, we're going to start taking a look at a introduction into chemical thermodynamics. In this video, we're going to look a lot at reviewing what we did earlier in the year when we talked about thermochemistry and just getting some definitions under our belt. So as you remember from chapter 5, we talked a lot about how energy cannot be created or destroyed. Right? The total energy in the universe is going to be constant. It can, however, convert from one thing into another. So, for example, from surroundings to systems. So we looked a lot at that when we were talking about heat and using the MCAT equation and all of that, looking at the transfer of energy. So when we did that, we focused mostly on enthalpy. Now, as a reminder, enthalpy is the heat absorbed by a system, right? And this is going to happen during a constant pressure process. Now, on the flip side, we have something else. We have something called entropy, right? So not enthalpy, but entropy. So entropy is going to be the measure of randomness in a system. And we're going to see that when we look at states of matter. We're going to look at how the entropy can vary from compound to compound and working our way from there. Both of these play a role in determining whether a process is going to be considered spontaneous. So spontaneous reaction is something that happens without any outside assistance. So for example, you drop an egg onto the counter, the egg's going to break, right? That process is spontaneous. What is not spontaneous is the reverse. Those eggs are not going to fly up off the counter, reassemble themselves in their shells, and go back into your hand. So we'll see reactions as we talk about them, both spontaneous things that will happen on their own and not spontaneous things that won't happen on their own. Another example is in a system that looks like this one here, where you have a bulb with a gas and one that is evacuated. Maybe there's no gas inside. So if we open the stopcock in between, we'll notice that the gas will spontaneously flow from A to B, and we'll see those pressures even out. What we're not going to see spontaneously is once we open the system, is that the gases are all going to stay in the one side and keep the other side empty, right? It's not whether A is totally filled or B is totally filled. That process where the gases are not random is not going to be, it's not going to happen. It is not spontaneous. One of the things we see with spontaneity is the effect on temperature. So if the best way to describe this is by looking at the act of water freezing into ice or in vice versa. So if I have a chunk of ice and the temperature is above 0 degrees Celsius, we will see that water melt from ice into water. What we're not going to see above 0 degrees Celsius is water freezing back into solid ice. We will see that process spontaneously happen, though, once the temperature drops below 0 degrees. And again, the reverse won't be true, right? Ice is not going to melt at, say, negative 10 degrees Celsius. So the direction of the spontaneity of a chemical process very much can depend on the overall temperature of the system. Some of these we're going to see as reversible and irreversible processes. Right, in a reversible system, something that can be returned exactly back to its original state, and it maximizes the work done on the surroundings. Where irreversible, we're going to see that any process that's spontaneous is going to be irreversible, where it's going to go from one state to another, and it's not going to be able to be undone. Now, entropy we're seeing is the thought of measure of randomness in the system, right? It is a state function. So one of the most common ways that we see this talked about is this type of equation that we've been working with all year long, right? The change in S being entropy, is going to be the entropy of the final system minus entropy of the initial system, right? That delta S, final minus initial. And we see that over and over and over again in all these calculations we've been doing. We also can see it from heat transfer, the heat of the reversible reaction over a constant temperature, although we don't usually work with that equation quite so much. Now, just to give a little bit of background on this, entropy itself is a huge field. There's a lot you can study with it. A lot of it ties into statistics too. And Boltzmann is actually one who really took a look at this on a molecular level. So, for example, if you have two molecules and you want them to be on the same side, right, there's a 1 in 4 chance that if you release them that way, they're going to end up back in that same organization. Um, that's fine, that's dandy, but the chances of us actually only working with two molecules is going to be pretty slim. More commonly, say if we have a mole of molecules, right, the chances of everything ending up back in the same state that we started in is, well, if there's only two possible states, is 1/2 to the Avogadro's number, right? 1/2 to 6.02 times 10 to the 23rd. So basically no chance, right? That the number on that is absolutely astronomical. So when we're looking at spontaneity and organization of molecules, we're seeing that the randomness of molecules does play a really big role into how we look at things. We're also going to see that the randomness of molecules is dependent on temperature and depending on the state they're in. So something like a gas is going to spontaneously expand to fill up the volume of its container, whereas something like a liquid, right, has a lower entropy. And while the molecules might be randomized, they're going to be randomized in a smaller volume, hanging out towards the bottom of a container. And in solid form, those molecules are going to have even less entropy as they're locked into a given position in a solid crystal. So I know this is a lot of terms, a lot of definitions. This is just meant to give you an introduction into what we're going to be talking about next. But if you have any questions, let me know. Thanks for watching.